Okay, good morning, everyone. So, for today, we will continue with the power analysis, the Parseval theorems. So, from the chapter 4, you know that in order to find the Fourier transform, first of all, you have two methods. The first one is the via the definitions, means that you use the formula. Okay, and the second one is you have to use the properties. So there are a lot of properties, more than 10 properties. So you got to familiarize with this all the properties. This is because when in the later section, you need to find the inverse Fourier transform. Means you need to find the xt from the x omega. Okay, the inverse Fourier transform, especially using the partial fraction expansion, you got the a b of c value, and then you got the x omega. So from the x omega, you need to transform back to the xt. So from there, you need to familiarize with the properties. Okay, you need to familiarize with the properties so that you know, okay, uh, this type of the omega domain is which time domain. Okay, if you don't know, not familiarize, this means that you don't know which properties or even use which Fourier transform of the pair table. Okay, so this is very important. So apart from that, we also use the Fourier transform to solve the application problem. Application problem is the circuit, especially the RLC. Okay, resistor, capacitor, and the inductor. Okay, either it connect parallelly or it connect series. Okay, so yesterday we cover until circuit analysis. Okay, circuit analysis. So today we'll cover the power analysis in terms of Parseval theorems. So based on these Parseval theorems, there are a few formula that you need to know. Okay, so first of all, this one, this is the if the this is the power associated with the signal. The energy carried by the signal is we call it omega. No, not omega. It considered as W. W equal to the integration from infinity minus infinity to infinity PT. PT is the power associated with the signal. Okay. For the 1 ohm of resistor, so this is the formula from the integration from minus infinity to infinity, x square. Okay, x square, xt square. Okay, and then from the Parseval theorem also said that, okay, the same energy can be calculated in the frequency domain. Okay, this is in time domain. Okay, you see that there's integration xt dt, but this one is in the frequency domain. So frequency domain is the formula is 1 over 2 pi integration from minus infinity to infinity x omega square d omega. So this is the formula in time domain. This is the formula in frequency, the omega domain. Okay, let's look at the example. Example 4.24. The voltage across a 10 ohm resistor is 5 exponential power of negative 3t ut watt. Find the total energy dissipated in the resistor. Okay, so let's go. Okay, there's a typo here. Can you please, for the frequency domain, can you just slash down the 0 here? 1 over 2 pi only for the 1 ohm, not 10 ohm. 1 ohm. Okay, so I stop sharing for this, then I will on another sharing screen. Can you see my screen, class? Okay or not?
Yes, doctor.
Yes,
Okay, yeah?
doctor.
Okay, Okay, example 4.24. Okay, 10 ohm resistor. Okay, and the input is V equal to 5 exponential power of negative 3t ut. Okay, so first of all, we find the energy carried by a signal in the time domain. So in time domain, okay, so we want to find out the energy at the 10 ohm. Okay, so 10 is the like amplitude, so we can it's a constant, and then the formula is from minus infinity to infinity x square, okay, xt square dt. So this is in time domain. Okay, you still remember just now I told you you can use in time domain. So 10 you integrate. Okay, since it's ut, so the limit is from 0 to infinity. Okay, so you have 5 exponential, so 5 square, 5 times 5 is 25 exponent power of negative, okay, 3t square is negative 60, negative 60 dt. So 10 times 25 you got 250, and then you integrate, okay, the exponential negative 60, you get divide by negative 6 from 0 to infinity. So therefore you get 250 divided by 6. This is, okay, exponent power negative infinity minus exponent 0. So this one you get 0, this one you get 1. So total is 250 divided by 6. So if you divide, you get 41.67 joule. Okay. So this is in time domain. What if we find in frequency domain or in omega domain? So in frequency domain, for the energy at 1 ohm, okay, is 1 over 2 pi. Okay, this is the formula lah. From minus infinity to infinity, x omega square. Okay. So from the question given, we know that Vt is 5 exponent negative 3t. So can you tell me what is the V omega? If Vt is 5 exponent negative 3t ut, okay, negative 3t, that's enough here. Okay, so what will be the V omega? Class, anyone tell me? From the time domain change to frequency domain. You still remember? You use the Fourier transform pair table. Class?
Remember.
So it's 5 divided by j omega plus 3. So that is the V omega you transform from the Vt. Okay? So because you know why you need to change? Because just now you want to do it in time domain. That's why we use the Vt in time domain. Okay, but the second one is we want to use it in frequency. We want to change to a frequency domain. So of course the Vt you need to change it in the frequency domain first. Then only we can use it, because the formula of this energy carried by the signal is x omega. So we need to change it to the uh, frequency domain before we can use it. So okay, now we know the V omega. So this actually the X omega is referred to the V omega lah, because refer to this question is referred to the V omega. So X omega square, okay, or in this case is V omega square equal refer to the X omega Okay, convolute with the x omega multiply with the x omega square conjugate. So what will you get? 5 over j omega plus 3 5 times j omega minus 3 because of the conjugate. So we get 25 j omega square plus minus, because minus 3 plus 3 and then minus 9. Okay, so if we know that j square equal to negative 1, so there will be negative omega 2 minus 9, or we can write in another way, 25 plus a is a plus or minus, plus negative negative. Okay, okay, what is next? Okay, we need to find out the omega, the energy for 10 ohm. Just now we find the energy for 1 ohm. Well, what about the energy for 10 ohm? Can you guess? Can you guess, class, how to do it? Okay, so what is next? So omega, the W for the 10 ohm is for the 10 divided by pi. Okay, 10 divided by pi, because we are talking about the 10 ohm uh, resistor. 0 to infinity x omega square d omega. Okay, first of all, there is something wrong here, because the box is 25 minus omega plus 9. Negative 1. Let me rewrite again. This one is 5, right? 5 over 3 minus j omega 5 over 3 plus j omega, because of the conjugate. Okay, So we have 25 9 plus 9 minus j omega square. So we have 25 j 9 minus j omega is -1, so negative square, so we got 25 over 9 plus omega square. Okay, so we have okay, omega square, we know that is 25 divided by 9 plus omega square, so we have 10 over pi integration. Okay, we have 25 over 9 plus omega square d omega. Okay, class, can we integrate directly? Can we integrate directly?
No.
Cannot, right? So if we cannot integrate directly, we need to change it. So how to change it? We have the formula. Integrate integration u prime x divided by 1. Okay, let me write it in here. U prime x divided by this 1 plus ux squared. So this is the formula, which is equal to the inverse tangent ux. Okay, this is the formula. So okay, we need to fulfill this type of the format, then only we can use this formula. So how? So from 0 to infinity, okay, if we want to fulfill this formula, u prime divided by 1 plus ux squared. Okay, so this in our from the our equation, 25 is just the what we call it, just the constant. It's just a constant only. So we just take out the 25. So we have 25 times 10, you got 250 divided by pi. Okay, this is 1 over 9 plus omega square d omega. So we need to change to the format. Okay, we need to change to u prime equal to 1 over ux squared. So it's 9. 9, we can factor it out the 9. So we just left 1 plus, okay, because we want to fulfill, right? So 1 plus, so we assume that we take out the 9, so we left 9, factor it out, so we got 9 multiplied with 1 plus omega over 3. Okay, this is square, so that we still have obtained the same thing. If we multiply in, we still obtain 9 plus 9 omega square divided by 9, but cancel out, you obtain 9 plus omega square, right? So it's the same value, so we just change the format only. Then d omega. So from here we know that, okay, if you compare with this formula and this one, we know that the u prime, the ux is equal to omega over 3. Okay, if we compare these two, the formula and what you obtain here, you know that the ux is omega, okay, omega over 3. So what is u prime? You differentiate it, you get 1 over 3, right? So with this 1 over 3, you need to put it here, because this one is the formula. Okay, so what you can get here? So 250 divided by pi. Okay, and then multiply with this is 1 over 9, this is 1 over 9, we can take out, so we can take out the 1 over 9. And then what else? The integration from 0 to infinity, 1 over 3, which is you obtain from here, divide by 1 plus omega over 3 square d omega. Okay, if you notice that this one is an extra, right? This one is an extra. So how to cancel out? So to cancel out the extra, the 1 over 3, so we must time with 3. So what is mean here is you need to multiply with 3. So this 3 and this 3 can cancel out. Okay, can cancel out. So means that we still get back the original signal like this one. Okay, we still get back the original like this one. Like this one. So what we get now? 250 divided by pi multiply over 3. Okay. Okay, no. So now let's check whether this what we obtain here is it fulfill the formula. If you look at the formula here, the integration u prime divided by 1 plus ux square equal to inverse tangent ux. So if we look at the what you obtain here, you change the format, is this is the u prime, okay, divided by 1 plus, okay, ux square. Okay, so this means that this part I can change to what? Change to the formula inverse tangent, right? So I can change to inverse tangent ux. So this one and this one cancel, I can get just 1 over 3, and then I get inverse tangent omega over 3. Okay, omega over 3. So this part is the part that I need to substitute with the value. Inverse tangent, okay, inverse tangent omega over 3. What do you get? You get pi over 2. Okay, so you obtain 250 divided by 6. This one can cancel out. So you get 41.67 joule. Okay, class?
Kita boleh ulang tak?
Apa?
Tak faham.
Ulang yang mana?
Start dari atas je.
Okay, for this question, the question asks you to find the total energy dissipated in the resistor, right? And the question given is only 10 ohm resistor and the voltage. Okay, this voltage is Vt equal to 5 exponent. You boleh nampak cursor tak? Cursor boleh nampak tak? Can you see my cursor? My mouse cursor?
Tak ada.
You can't see my cursor? Oh, okay, never mind.
No.
Okay, never mind. I just try to use the highlight if possible. Okay, so this is the Vt. This is the Vt given by the question. So first of all, you need to find in time domain. So what is in time domain? Okay, in time domain, this means that the energy carried by signal, okay, use this formula. Okay, this is the formula. Okay, so you just substitute because the xt actually is equal to the Vt. So xt square, okay, 10 is referred to the resistor 10 ohm. Okay, 10 ohm. And then x square is referred to the 5 exponent power of negative 3t. When you square it, you get 5 times 5, you get 25. Okay, exponent power of negative 60, because negative 60 times 2, you get, and negative 3t times 2, you get negative 60. So, and after that, you perform the integration, you get here. Okay, get this one. Okay, substitute the value. You substitute the value t with infinity and 0. So you got 0 and 1. So from here to 250, okay, multiply, divide by 6, you get 41.67 joule. So this is in time domain. So the question said you need to find the total energy. Okay, either you can use the in time domain or you can use it in frequency domain. Both will get the same answer. Okay, you can solve it in time domain, or you can solve it in frequency domain. Okay, if from this case, of course, you solve it in the time domain, it is easier. Okay, definitely is look easier. So if I also show you in solve it in the frequency domain, okay, so that you have the choice. Okay, you solve it in frequency domain. So first of all, let you know that in order to find the energy carried by signal, okay, for the 1 ohm, this is the formula. For 1 ohm, this is the formula. Okay, and then if you want to find in frequency domain, so everything Vt you need to change to V omega, because in time domain, right, and in frequency domain, you change to V omega. So this one you through the Fourier transform pair table. Okay, since the formula is x omega square, so x omega square equal to x omega multiply with x omega conjugate. Okay, so x omega and x omega conjugate. Conjugate means the sign inside is one is positive, one is negative. That's it. So you obtain from the x omega and x omega conjugate is 25 divided by 9 plus omega square. Okay. So now we want to find the omega in we want to find the energy. Okay, energy in 10 ohm. Okay, so this is the 10 ohm, 10, and then this is the input lah. So where we obtain from the previous calculation. So 10 divided by pi integration, because from 0 to infinity, because this one is a ut, so 0 to infinity, and x omega is from here. Okay, so if integration 25 1 plus 9 square 9 plus omega square is you need to use a formula, you cannot straight away. Okay, but normally we don't have the pecahan like this, right? We only have one exponential, only we don't have the numerator or denominator, we just have one. So this is quite seldom you see this type of example lah. Okay, so in order to solve using this integration, so there's a formula. So this is the formula. Okay, this is the formula. Okay, in order to use this formula means that this is in order to use this formula, you need to fulfill this formula. So this formula is integration u prime divided by 1 plus ux square. Okay, then only you can use inverse tangent ux. If the format of this formula is not fulfilled, you cannot use inverse tangent ux. Okay, so in order to use this, you need to fulfill. Okay, fulfill. So how to fulfill means that you need to change the equation that you have, same type as this formula. Okay, so if you look at this one, if you look at this 25 over 9 plus omega square, this 25 actually is just the constant. Okay, it's just the constant. So you can take out the constant. You can take out the constant. Wait. Okay, you can take out the constant. So 25 times 10, you get 250 over pi. Okay, so you just left 1 over 9 plus omega squared. Okay, 1 plus 9, 1 over 9 plus omega squared. So just left this one. So from 1 over 9 plus omega squared, you need to change to this format. Okay, this formula format. So from the formula, okay, denominator is 1 plus. So I try to change to 1 plus something also. So I factor out the 9. So I got 9. So I factor it out, this one. So I got 9 uh 9 in the bracket, 1 plus omega over 3 square, which is the same value. Okay, if I multiply it, I still get the same value as this one. I just change the format only. Okay, so this is the things. And then in order to use formula, we also need to change to the u prime. So based on this ux, you differentiate, so you get u prime. That's why I said if ux is omega over 3, u prime is 1 over 3. So therefore, I put here 1 over 3. Okay, I put here 1 over 3. Okay, just to fulfill the format of the formula. But if I put 1 over 3 here, but this one is the extra. Do you know why extra? Extra means that it's not the original value of your equation, because your equation is 1 over 9 plus omega squared. But now it's 1 over 3. So I don't want this extra. I want to keep the original value. So I cancel out by multiply with 3. So I multiply with 3, I still obtain the value is 1. Therefore, I multiply with 3. So now this whole things is fulfill the formula. Okay, fulfill the formula. So I can change to this. Okay, you still remember? I fulfill, then I can change to tangent ux, inverse tangent ux. Okay, but I still copy down this one and this one. This one 1 over 9 multiply with 3, you obtain 3, 1 over 3. Okay, so since this is the integration, of course you have the limit from 0 to infinity. So just substitute in, so you get the answer. That's it. Okay?
Okay, Doctor.
Alright. Any other question?
So far, no, Doctor.
Okay. So if that is the case, we finish the chapter 4. Okay, we finish chapter 4. So I want you to do the tutorial 4.3. Okay, please do Q2, Q3, Q4, and then Q7. Okay, you do these 4 questions and submit on next week. Next week is, what is that now? 12. Okay, 12th of January. Okay, any question to ask?
Doctor, scroll atas sikit. Okay, thank you, Doctor.
Yeah? You done?
Okay, Doctor.
Okay, so if you have done, so I will continue with chapter 5. Okay, chapter 5, which is lecture 11 about the Laplace transform. So this is the last topic. Okay, last topic in signal and system, the Laplace transform. So Laplace transform also consists of definition, ROC, inverse Laplace transform, all this. Okay, so okay, just this one is to let you know we have three things. We have three lecture to cover in this chapter. The first one is finding the Laplace transform using definition. You need to find the inverse Laplace transform and the region of convergence. Okay, and then okay, as usual. Okay, if you the Laplace transform can find using definition, of course it can find using the properties as well, just like the Fourier transform. Okay, and lastly is the application question, means that you have to use the solve the circuit problem, LCCDE, broad diagram, causality, and all so on. Okay, so in this topic, in this lecture, we will cover just these few things: definition, what is a unilateral. This is type of the Laplace transform. You have two types: unilateral and bilateral. Okay, later I will explain more in detail what is unilateral and bilateral. And next is the inverse lah. Okay, inverse also can use the partial fraction and so on. And lastly is the region of convergence. So this is the man, okay, who introduced, okay, the Laplace transform. Okay, just to refresh back, okay, what you have learned before. Before this, you learned about the Fourier series. So this Fourier series is for what? Okay, this is for the study of signal and LTI system. And then you'll study the Fourier series in chapter 3. Okay, you'll study exponential Fourier series, trigonometric Fourier series, and amplitude phase Fourier series. Okay, in chapter 4, we are talking about the express the signal in a linear combination of complex, okay, sinusoidal, where the via the formula we know that the signal xt you have to multiply with the exponent minus j omega t, okay, which is in the omega domain. And for this chapter, you'll learn about the Laplace transform. So this Laplace transform actually is continuous from the Fourier transform, where this complex sinusoidal become a complex exponential. Okay, the complex sinusoidal change to complex exponential in the form of exponent negative st. So in this topic, you won't see any omega domain, but you will see in s domain. Okay, and then this Laplace transform is used to convert the integral and differential equation into algebra equation. Okay, this is the two type of the Laplace transform that I explained to you just now. Unilaterals means that it's just one side a Laplace transform only, which is starting from 0 to infinity. Okay, you still remember the limits? Okay, the integration either from negative infinity to infinity, or 0 to infinity, or negative infinity to 0. But unilateral is referred to one side Laplace transform, which is the t is more than 0. This means it's from 0 to infinity. Why is someone clicking the...
Doctor,
Yep,
excuse me, Doctor. Are you moving any slide?
yes.
Because we doesn't see the slide moving.
You didn't see any... Oh,
Uh, okay, thank you, Doctor.
sorry, I not realize it. Okay, thanks for informing me. Okay, can you see the slide now?
Okay, doctor. Thank you, doctor.
All right. So, okay, this is the type of the Laplace transform that I explained to you just now, like unilateral. Okay, one side, this is the one side Laplace transform. Okay, and then it's commonly used in causal LTI system, means that it's designed for the feedback and control system. Okay, for the bilateral Laplace transform, bilateral means two. So two-sided. Two-sided means that is from negative infinity to infinity. It could be from negative infinity to 0 and plus with 0 to infinity. Okay, so this is useful for the study of system, especially the stability and causality. Okay, so for the bilateral Laplace transform, okay, if you look at Laplace transform, uh, the symbol, okay, the symbol of the Laplace is like a L. Okay, Laplace is like L. B is referred to the bilateral. Okay, so Laplace transform of the time domain become the S domain, XS. Okay, S domain. Okay, so bilateral is from negative infinity to infinity, xt exponent power of negative st. Okay, if you look at the Fourier transform, is xt multiplied with exponent minus j omega t, right? Minus j omega t. Now, in the Laplace transform is minus st. Okay, minus st. Where the s here is referred to sigma plus j omega. This is the complex number that you talking about lah. Okay, complex exponential, which is explained here. Okay, so the integral limit is from negative infinity to infinity. For the unilateral Laplace transform, it is from negative infinity to 0 plus 0 to infinity. Okay, so this is bilateral. This is unilateral. No, I think this one is bilateral. This one is still bilateral. Whereas this part only unilateral. 0 to infinity is unilateral. Okay, Laplace transform bilateral is from negative infinity to 0, 0 to infinity. So this one actually is a combination, is continuous from the bilateral. This means that the limits from minus infinity to infinity can be split into negative infinity to 0 plus 0 to infinity. Okay, for and then the lower part, this lower part only refer to the unilateral. So unilateral refer to the t that more than 0. That's why it's range from 0 to infinity. Okay, integral limits. So on the point of discontinuity, a function st can take two value, so plus or minus. Okay, later you need to test more than 0 or less than 0 for the limits as well. Later I will tell you what's meant by. Okay, uh, this is this is just a relationship between the Laplace transform and Fourier transform. Okay, so just now I told you that the S is referred to the sigma plus j omega, right? So if we take out the exponent power of negative omega t from the exponential, we left xt exponent negative sigma t exponent negative j omega t. So this one, so xs is the Fourier transform of this. So so this means that this Laplace transform is actually generalized from the Fourier transform. It's interrelated. So generalizing the Fourier transform, the extra factor of exponent negative st is called the convergent factor. It's called the convergent factor. Okay, let's look at the example. We go to the module. Okay, 5.1. Find the Laplace transform of xt equal to AUT. Okay, this one is okay. Never mind. I explain using the my own explanation. So just look at this example. Find the Laplace transform of xt equal to AUT. So I stop sharing and I share via my iPad. Okay. So exponent xt equal to AUT. This is referred to the amplitude is equal to A for t that is more than 0. Okay. So Laplace transform of the xt is equal to xx. Okay, because in the s domain. So this means is from negative infinity. Ut. Okay, so ut is from 0 to infinity. Okay. Okay, never mind. We write it the formula first. This is a formula, so you can familiarize with the formula first. Okay, this is the formula. So and then I substitute in the limits is from 0 to infinity. Xt is a. Okay. Okay, a is a constant, so I can take it out. And then I integrate. Okay, I integrate. Okay, what can I get? So this is 0. Okay, so negative 1. Negative 1, I obtain positive a or negative, negative. No. Okay, so this is negative 1. Negative a over s. Limits t goes to infinity, e minus st minus e0. So normally the normally we write the exponent negative infinity in limits exponent negative power st and then t goes to infinity. This is the correct way we write it lah. Okay, so next we have two conditions. Okay, the first one is s, we need to test s more than 0 or s less than 0. Okay, so we need to test it first. So if s less than 0, what will happen? If s less than 0, okay, let's say if you look at this one, when the s here, when the s here less than 0, means that you will obtain negative value. Correct or not? This means, okay, for example, if s less than 0, if s less than 0, this means I put a value. Okay, for example, I have negative s. Okay, s less than 0 means it's a negative s. So if exponent negative s t like this, then minus with 1. So what do I get? This will become exponent positive infinity, because negative s is a positive s, st. Positive st, when the t substitute with the infinity, so this will go to the infinity. But if s more than 0, if s more than 0, this means that this is limits t goes to infinity. Okay, if s is more than 0, it means it's a positive s. So it's positive s. So if the if this t is changed to infinity, so what will you get? Negative infinity. So negative infinity will obtain 0. So you obtain a over s. You got it, class? Faham tak?
Again, Doctor?
Okay, so if I want to change you from totally Fourier transform to Laplace transform, you need some time. Okay, so first of all, you need to know is Fourier transform is in omega domain. Yes, and then Laplace transform is in S domain. Okay, so in S domain means that in Laplace transform you need to test, okay, the limits. Okay, you need to test whether the s is more than 0 or less than 0, because if s is more than 0, you have different value. Less than 0, also different value. So first I want to ask you, if up to here, are you okay? Sampai sini boleh kan? Ya, understand kan?
Sini okey.
Sampai sini okay kan?
Okay, Doctor.
Okay, so maybe you want to ask, why I need to consider two conditions? Because if I only have one conditions, the s could be from negative infinity to infinity. And then if I have positive infinity, I will got a different value. If I have negative s, I have the different value. Okay, because of what? Because when you substitute the t with infinity, you also know, right? Exponent negative infinity, you obtain 0. If exponent power of positive infinity, you will get infinity. So this is the difference. So if you get negative, you will get negative infinity, the answer is 0. If you have positive infinity, the answer is infinity. So that's why you need to test the two conditions. Either the s here is more than 0 or less than 0. That's why I said if s less than 0. Okay, if less than 0 means that the negative s. Am I right? Betul tak?
Yes,
Okay,
Doctor.
negative infinity. So from here, I just substitute. If the s is less than 0, okay, so I substitute the value of negative s. So, and also substitute the value, I substitute the value of negative s. So, the negative st, so means that is a positive st. Positive st, and this t is referred to the infinity. So, positive st, so I obtain the exponent power of infinity lah. Okay, minus 1, because infinity is huge. So if minus 1 is still infinity. Okay, so the answer is the infinity for s less than 0. What if s more than 0? If s more than 0, okay, I substitute the s with positive s means that I have the positive s. Okay, if positive s, exponent power of the negative s multiplied with t, the t is the infinity. So I got negative infinity is 0. 0, okay, minus 1, I got negative 1. Negative 1 multiplied with negative a over s, I get a over s. So if you compare, I get different value for the, okay, if s less than 0, I got answer is negative infinity. If s more than 0, I got the value a over s. That's why you need to test. Faham tak?
Okay, baru faham betul.
Okay. So you can rewrite all the question again. Okay. So this is the first question. Okay. Second example, you go to example 5.2. Example 5.2, you need to find the Laplace transform for the xt equal to 1. So Laplace transform of the xt is from 0 to infinity e minus st, okay, multiply with 1 dt. So integrate the okay, you integrate is from 0 to infinity. Okay, it looks simple. Again, you still have two conditions. Okay, two conditions where the s here either more than 0 or s less than 0. Okay, let's test. If s less than 0, so you have 1 over s. Okay, you multiply exponent. Okay, so now you substitute the s with negative s. So it's negative s t. Okay, so what do you get? So it's positive infinity. So positive infinity, of course, you will get infinity. So you test for the s, which is more than 0. So negative 1 over s. Okay, exponent no, the positive s, so it's a positive s t, okay, minus exponent 0. So in this case, you will get exponent negative infinity because this one is changed to infinity. Alright, so negative minus 1. So this one you will get 0. So you get positive 1 over s. You can see that there's two different answer for more than 0 or less than 0. Then lastly, you write out the final answer. Okay, class? Boleh ikut?
Boleh doktor.
Okay. So the example after this all got the positive and negative. Okay. All have these kind of things. Okay, let's look at another example. I just want to familiarize with you. So example, I think this one is 5.3. Okay, find Laplace transform of exponent power of at. So Laplace transform of exponent power of at equal to 0 to infinity exponent. So most of the time we only use the the range, the limits is from 0 to infinity. Okay, so if you look at here, you always see I use the limits is from 0 to infinity. I think the front part to substitute is not the problem. The problem is when you test for the s more than 0 or s less than 0. But it's not all the time s is more than 0 or less than 0. So this question, I will show you what's mean here. Okay. It depends on the question as well. Okay, if you look at here, class, if you look at here, it's a minus s. Just now, it just s only, right? It just s only. Okay, it just s only. Okay, but current question is a minus s. So you have to follow the question. A minus s is equal to 0. So s equal to a. Okay, so this means what? So test for s more than a and s less than a. Alright? So if s less than a, let's say we have let's say one value lah, s equal to 5. Let's say, just assume only a is equal to 10. So a is equal to 10. So it means that a minus s, what will you get? Will you produce positive or negative value? 5 minus 10, 10 minus 5. Let's say this is 10
Positive.
minus 5. So it's a positive value, right? So you will get positive value. Okay, you get positive value. Okay, 1 minus a. Okay, it's a positive value. Okay, positive value. So this one I substitute with infinity minus exponent 0. So what do you get? What's the answer? This one is infinity, right? This one is 1. Okay, so of course, when infinity, of course, is very big infinity. Boleh ke? Boleh ikut? Faham tak yang ini? Do you understand? Before I move to another condition, just let me know if you not understand.
Okay.
Hmm.
Ni ulang balik tak, Doktor?
Yang mana?
Yang kita assume yang nilai tu, Doktor.
Okay, up to the black color, you okay, right?
Okay.
You off the mic first. Okay, so up to here is just normal. Okay, so that's why I tell you is the problem whether you want to test what. Okay, you have to refer to the question. Okay, that's why I said this one a minus s. Okay, because from the question is the question give you exponent power of at. Now you substitute the input, you obtain, okay, exponent power of a minus st, okay, in the bracket at t. So now it's a minus s. Okay, a minus s. So you need to test for a minus s. Okay, so I put here a minus s equal to 0. Okay, so I move the a to the right hand side. So s equal to a. Okay, s equal to a. So I can test s more than a or s less than a. Ataupun you nak buat a tolak s more than 0 or a tolak s less than 0 pun boleh. Up to you. Okay? Mana-mana lah. Faham tak?
Faham, Doktor?
Okay. So, let's say in this one I test for if s less than a, and s more than a. If s less than a, I give you a number so that you can see it clearly. So let's say s is equal to 5, a is equal to 10. So a minus s means that it's 10 minus 5. Do you get positive or negative value? Just now you told me you get positive value. Okay, so that means that a minus s, you will get positive value. So when you get positive value, okay, so here you just substitute with the positive value lah, a minus s. Okay, you multiply with infinity, so exponent infinity, you get infinity. Okay, so that is how you get infinity. Okay, you now try for if s more than a. Okay, let's say s is equal to 5, a is equal to 3. So a minus s will produce positive or negative?
Negative.
A is 3, s is 5. Okay, you will get negative value. So this is 1 over a minus s. Okay, negative value means that you have the negative here, a minus s. Faham tak? If I set positive value, this is positive. Positive, this is a positive. Negative, you have the value negative here. Okay, hope you can understand the difference. Okay, and then you multiply with the infinity. So what do you get? This one, of course, exponent negative infinity is 0. Faham tak? You okay? Okay or not, class? Hello? You need time to digest?
Ya, doktor.
Huh?
Boleh doktor.
Boleh ya? I think maybe that if you want to easy to understand, maybe you can refer to my notes because in the example in the module they straight away direct. You don't know what happened. You straight away you get the answer, or probably you don't understand how to get it. If you refer to my notes, you can see okay how many conditions, how to test, all these things. Okay. Okay, we go to example 5.4. Okay, also the same. Xt equal to exponent negative at ut. So Laplace transform of exponent negative at from 0 to infinity, exponent negative at, exponent negative st. So you combine. Okay, then you integrate. For this case, it's slightly different. Okay, what is the difference? If you look at here, the original equation here is already negative. So you need to be careful. Already have the negative in front. If you look at the previous question, the previous question is original is positive. Okay, so it makes different for the final answer. Okay, so now you see that it is negative s negative s, negative a. Am I right, class? From here. Negative s, negative a, okay, equal to 0. So I want to test for the s equal to negative a. I move the s to the right hand side. I get s equal to negative a. So I test for s more than negative a and s less than negative a. So let's say if s more than negative a, so I have 1 over negative s plus a. Okay, so if s more than negative a, okay, I will get positive or negative. Let's say I assume s is equal to 10, a is equal to 5. So what do I get? Get positive or get negative?
Positive, Doctor.
Positive. Okay, get positive. So you get positive, you remain. So this one is negative infinity is 0, so you get 1 over s plus a. Alright, what if s less than negative a? Let's say s is equal to negative 10, a equal to 5. What do you get?
Negative, Doctor.
Okay, s is negative 10, a is 5, so you get negative. So negative means that you have negative and you have another negative, right? So negative, negative, you get positive. So you get positive infinity.
Infinity.
Yes. Okay? So therefore, so you copy down the final answer. You okay?
So far, okay, Doctor.
So far okay, huh? Okay, I explain one more question before we stop. This is example 5.4. No, 5.5. Example 5.5, the xt is cos omega t. Okay, you know that the xt is cos omega t, so you can change to exponential. Okay, you can change to exponential. This is the exponential form. So then you can start do the Laplace transform. Okay, so this is as usual. Okay, you combine the exponential. Okay, for this one, I integrate, I obtain negative s minus j omega. This one I exchange the location, class. I just now I accidentally this. I exchange the location only. Okay, and then okay, this one you can substitute the t value. Okay, whether s minus j omega. So you need to okay, let me see. S minus j omega. So you get negative infinity. And then this one is negative in omega minus 0. So this one you get 0, this one also get 0. Okay, after you simplify, this one is with the case the s is more than 0. Class, we take the condition for s more than 0. One over s minus j omega plus 1 over s plus j omega. So you want to sin the denominator. So you have s plus j omega over s minus j omega, s plus j omega. And then s minus j omega, you have s plus j omega, s minus j omega. Okay, s plus j omega plus s minus j omega. This one. Okay, maybe I change a little bit. We can write it as s square, because s plus j omega, s minus j omega, we can change to s square minus j omega square. So j omega, j square equal to minus 1. So this one cancel out. You get 2s s square minus omega square. When cancel, you get s square plus omega square. So this one only valid for s more than 0. If you test for s less than 0, you will get infinity. So we only test for s more than 0. Okay, or not, class? So this is how we find the Laplace transform using the formula. Any question to ask? Okay, if no question, I want you to do the exercise. Exercise 5.1 in page 237. Okay, you do A, Q1A, A, D, and then G. A, D, G. Submit on 12 also. Right? Okay?
Betul.
Hmm.
So kalau kita dah tahu nilai tu kita dapat infinity. So memang tak payah buat dah tu.
Mm, you can test first lah, but like before, to be sure, right? Because if you don't know, if you don't test, you don't know. You can
Thank you,
test
Doktor.
first. This one already skipped the step of testing. But if previously you saw it, I test, right? Okay. If test, you will notice that there's one either more than or less than you will get value, and another one is infinity. So less than 0 or less than a, you will get infinity for most of the case. So we will put also, but it's not compulsory like this lah, because somehow it depends on the question. If the question you have negative, right, for example, exponent, if it, let's say okay, if this question is like this, okay, originally you will get a negative st. So of course when you test less than 0, you will get infinity. Then more than 0, you will get a value. Okay, for this question, the question given is this like this. Okay, then you test less than 0. You boleh nampak kan kelas? Boleh nampak kan? Okay, if less than 0, you will get infinity. If more than 0, you will get the value. But there's a different case like 5.3. Okay, 5.3. Okay, this one you get less than 0 infinity, more than 0 is value. Okay, this one also the same. But this one I think is this question. Okay, this question, if you test more than negative a, you have value. Less than negative a, okay, this one also the same. This one also the same. I think you have to test first lah, to be sure. Okay, if you find out the value, okay, if the latest one, right, this question, cos omega t, this one you can test also. This one you can test. Okay, at which test you can test? You can test here, this part. You test if s minus j omega is more than 0 or less than 0. Okay, then only you can proceed. But less than 0, you will get infinity. Okay?
Okay, Doktor. Thank you, Doktor.
Alright, so I think it's time now. So I just stop here and we take the attendance.